Have you ever looked at a straw in a glass of water and thought, why does it look bent at the surface? Or why does a coin at the bottom of a bucket appear to be at a different place when you look from above? Well, these curious effects aren't tricks of your eyes, they're the result of a fascinating phenomenon in physics called refraction. When light passes from one transparent medium to another, say, from air into water, it usually changes direction at the boundary. This bending happens because light changes its speed as it moves between media of different optical densities. Scientists have studied this for centuries and found that this bending isn't random. It follows very precise rules called the laws of refraction, also known as Snell's laws. These laws mathematically relate the angle at which light enters and the angle at which it bends inside the second medium. And yes, the amount of bending depends directly on how much the optical density of the two media differ. Let's start with the first law. It states the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. This means that if you draw them on paper, they will always be in the same flat surface. There's no jumping out into another dimension. Whether the media are air and glass, water and air, or even diamond and air, the geometry remains the same. Why is this important? Because it ensures we can predict the path of light using simple two-dimensional ray diagrams. As the diagram shows, you can see the incident ray approaching the surface, the refracted ray bending inside the medium, and both sharing the same plane along with the normal. The second law of refraction is more mathematical, and this is where the magic of calculation begins. It says the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. Mathematically, we say sin I divided by sin R equals mu sub 1 2. Here, mu sub 1 2 or mu 1 2 is the refractive index of medium 2 with respect to medium 1. This constant depends only on the two media, not on the actual values of I and R you choose, as long as both are measured for the same pair of materials. With Snell's law, if we know any three of these quantities, I, R, and mu, we can calculate the fourth with accuracy. On the diagram, you'll see the angles marked I and R, the normal, and the sine ratio written alongside. Now, what exactly is this refractive index? The absolute refractive index of a medium tells us how much slower light moves in that medium compared to vacuum or air, since air's refractive index is nearly 1. The formula is simple, N equals C divided by V, that is, refractive index equals the speed of light in vacuum divided by the speed of light in the medium. If the refractive index is higher, light travels slower inside that medium. For example, for glass, N equals 1.5. This means light travels 1.5 times faster in air than in glass. You can check the table in the slide. It lists common materials from water to diamond and their refractive indices. Sometimes we want to compare the speed of light into media directly without referring to vacuum. That's when we use the Relative Refractive Index, denoted mu1 to it's given by the formula mu1 to equals v1 divided by v2, where v1 and v2 are the speeds of light in medium 1 and medium 2 respectively. It can also be written as mu1 to equals n2 divided by n1 using the absolute refractive indices. For example, the refractive index of water with respect to glass is 1.125. This means light is 1.125 times faster in water than in glass. As shown in the diagram, we can represent two media side by side with velocity arrows and the refractive index ratio connecting them. Let's apply this in a real calculation. Problem: a ray of light enters glass from air. The refractive index of glass is 1.5 and the angle of incidence is 40 degrees. We need to find the angle of refraction. Step 1. Write Snell's law, sin I divided by sin r equals mu1 2. Step 2. Substitute the values sin 40 degrees divided by sin r equals 1.5. Step 3. Rearrange the formula sin r equals sin 40 degrees divided by 1.5. This is approximately 0.428. Step 4. Take the inverse sin r is approximately 25.3 degrees. So, the ray bends towards the normal inside the glass, making an angle of about 25 degrees with it. In the diagram, you can clearly see the incident ray, the refracted ray, and how much it tilts towards the normal. Let's quickly revise what we've learned. Law 1. The incident ray, the refracted ray, and the normal are all in the same plane. Law 2. Sine of the incidence angle divided by sine of the refraction angle is constant for a given pair of media. We also explored the absolute refractive index, n equals c divided by v, and the relative refractive index, mu1 2 equals v1 divided by v2 or n2 divided by n1. These concepts are not just theory, they're used in lens design, microscopes, telescopes, optical fibers, and even in underwater goggles that correct for refraction when you swim. I hope you now have a clear picture of how light bends when entering different media and how we can measure and predict that bending using Snell's law. See you in the next session where we'll continue exploring the wonders of light.